An open box is to be constructed from a rectangular piece of cardboard measuring 100 centimeters by 120 centimeters by cutting out 4 equal squares from each of the corners. In part A, we want to draw a diagram to represent the construction of the box. So we can start with the rectangular piece of cardboard, which measures 120 centimeters by 100 centimeters, as shown. Next, we want to cut 4 equal squares out of each of the corners, and we're going to let the length be x centimeters for each of these squares. From this, we can determine what the length and the width of the box will be once it's turned into a 3D shape. So this here is going to be the length of our box. And the length of that blue line is 120 centimeters subtract 2x, because we've removed 2 lots of x when we cut the squares out. Which means the width over here will be 100 subtract 2x. Using our diagram from part A, we can find an expression for the volume of the box in terms of x. So we're going to call this function v of x, which is the volume, and we know it's equal to length, which is 120 minus 2x, by the width, which is 100, take 2x, by the height of the box, which is x when we turn up each of the sides. If we expand that, we get that the volume is equal to 4x cubed minus 440x squared plus 12,000x. For part C, we want to state the practical domain for x. So because this is a physical thing that we're making, it makes sense that x can only have a limited set of values to take up. So the first thing we need to think of is, can it be positive or negative? And because all the lengths are a distance, it needs to be positive. So we need x to be greater than 0, and then we need to look at our side lengths and work out what values of x make sense. So if we have a look at this 100 subtract 2x, it makes sense that that needs to be always positive. So if we think we need 100 take 2x to be positive, which means x cannot be bigger than 50. Because the minute you put a number bigger than 50 in there, it will become negative. Which means that our practical domain for x is going to be x is an element of 0 not included, because we need a 3D shape, all the way up to 50 not included, again because we need it to have a third dimension. So for part D, we need to find the largest possible volume the box can have. And in blue, we've got our expression for the volume in terms of x, which we found previously. So to find a maximum, we need to get the derivative, which is going to be v dashed of x, and let that equal 0. And that'll find any stationary points on our curve. So the derivative, we can use our power at the front, 1 off the power rule, and that will become 12x squared minus 880x plus 12,000. And we need that to equal 0 to find any stationary points. So we can use our calculator to solve that for us. On the CAS calculator, go into the main menu. Here we can enter our expression for v of x, which we found previously to be 4x to the power of 3 subtract 440x to the power of 2 plus 12,000x. If we highlight that, we can define it. And because it's the volume, we're going to use the ABC keyboard and give that the name v of x, which is our volume formula. Next, we can get the calculator to calculate derivative for us. So we go interactive calculation diff and press OK, and that's the derivative we found previously. We knew that to find any stationary points, which will be our maximum, we set our derivative equal to 0, and we solve that. So if we go interactive equation inequality solve, these are the solutions for our derivative equal to 0. We can also quickly check what their decimal values are. So the first one is 18.1 and the second one is 55.2, just to 1 decimal place. From our CAS, we found that the first solution for x was 100 subtract 10 times the square root of 31 over 3, and the second solution was x is 100 plus 10 root 31 over 3. We also discovered that as a decimal this was approximately 18.1 and this was approximately 55.2. And now remembering that our domain said that x needed to be between 0 and 50, we can see that this is not a solution to our problem because it's outside the domain. Therefore, we can calculate the maximum volume by substituting 100 subtract 10 root 31 all over 3 into our volume expression, which is up here. So we know that the maximum volume occurs at the first one of these solutions. So in the calculator we can easily calculate the volume by substituting in that first solution, and that will calculate what the volume of the maximum box is. So in this one we want a decimal answer, so we can convert that, and the calculator tells us that that is approximately equal to 96,770.58 centimeters cubed. We can also use the graphical feature of the CAS calculator to check that this is in fact a maximum. So if we go into the graph screen and we drag our expression of v of x down into the graph, you'll see that the graph's appeared in that blue line, but we can't really see it. So we can resize the graph screen by going to this menu, and we want to go between 0 and 50 as our practical domain of x values, and for y we want to go from a volume of 0 through to its maximum volume, which we found just before to be slightly less than 100,000. So if we put 100,000 here, we should get the entire graph. And to find that maximum, we can go analysis, gsolve, max, and that gives it at 18.1, which was the x value which gives the derivative equal to 0. And we can see that our y value, or the volume value, is 96,770.58, correct to 2 decimal places as well, which shows that this is in fact a maximum for the volume. Therefore, our calculator confirms that the maximum volume that this box can have is 96,770.58 centimeters cubed, correct to 2 decimal places.